Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous two lectures, we were discussing about basics of probability and statistics which are required for the analysis of hydrologic variables. Hydrologic variables, we have seen that it is involved with certain uncertainties. So, in order to deal with the variables which are having uncertainties, we need to treat that in probabilistic way. That is why we need to have the basics related to probability and statistics. So, very minimal way we have covered in the previous two lectures, that is the different types of random variables, that is variables which are involved with uncertainties are considered as random variables, and in that itself we have seen discrete random variables and continuous random variables. After that, we have seen what is meant by probability distribution, that is corresponding to each and every value taken up by the random variable, there is an associated probability. The relationship between these values and the probabilities is represented by means of probability distribution. In the case of continuous random variables, we will describe by means of probability density function, and in the case of discrete random variables, we make use of probability mass function. Then corresponding cumulative distribution functions also we have looked into. After that, we have discussed about the descriptive statistics which are required for hydrologic analysis. Those were of measures of central tendency, measure of peakedness, measure of symmetry, and measure of dispersion. Now let us look into different types of probability distribution functions which we commonly use in hydrology. Probability distribution function related to discrete random variable and also continuous random variable. So, we will start with probability distributions. Hydrologic variables follow certain probability distribution. Various probability distributions can be used for analyzing hydrologic variables. Various types of probability distribution functions are there, but depending on the type of the variable which we are dealing with, certain kind of probability distribution it will be following. So, majority of the probability distribution functions which we use in hydrologic analysis we will discuss here. Discrete probability distributions and continuous probability distributions. Discrete probability distributions are related to discrete random variable, and the continuous probability distributions are related to continuous random variables. In the case of number of rainy days, they will be taking integer values. Those are considered as discrete random variables. But in the case of rainfall, stream flow, etc., these will be taking a value within certain range. It cannot be expressed by means of an integer. It may be taking the fractional values also, that also within certain range. Those type of hydrologic variables will be considered as continuous random variables. The probability distributions which they follow are considered as the continuous probability distributions. Under discrete probability distributions, we will see binomial distribution and Poisson distribution, and under continuous probability distribution, we will look into commonly used exponential distribution, gamma distribution, normal distribution and Gumbel distribution. Normal distribution is also termed as Gaussian distribution. So, these are the distributions, probability distributions which we are going to look into in this lecture. First one is the binomial distribution. A binomial distribution is the probability of only two outcomes in an experiment that is repeated multiple times. That is, in this case, the outcomes are only two. You can consider the case of tossing a coin. So, what are the two different types of outcomes which you are expecting? One is getting a head and the second one is getting a tail. So, in both the cases, the probability of occurrence is the same, that is 0.5. When you toss, the probability of getting a head is 0.5. The same probability is there for getting a tail also. That value of probability is not changing, and at the same time we can expect only two outcomes, either a head or a tail. So, this is that kind of distribution in which we can expect only two outcomes for different number of trials. So, the outcomes can be termed as success or occurrence, failure or non-occurrence. That is, getting a head, if we are considering it as success, that is the occurrence of an event. After tossing a coin, probability of getting a head is considered as the success means, failure is probability of getting a tail. So, these outcomes are considered as success and failure, that is occurrence and non-occurrence. In the case of a flood, whether there is a flood or there is no flood, these are two cases, yes or no cases. There can be a flood in this year, there cannot be a flood. So, we are not quantifying the values, probability of occurrence of a flood, whether there will be a flood in the coming year or there will not be any flood. So, that can be represented by means of two outcomes, that is, one chance is that there can be a flood and on the other hand there cannot be a flood. So, these type of analysis can be done by making use of binomial distribution. The probability of occurrence is same and not changing one trial to other. Binomial distribution can be used to find the probability of occurrence of an event exactly r times in n successive trials. N times the experiment is conducted. In that, we are expecting the probability of occurrence of an event r times, exactly r times. Then we can represent that probability p n r by NCR p raised to r q raised to n minus r. NCR is the combinatorial representation. NCR can be represented by n factorial divided by n minus r factorial r factorial. So, NCR is represented here multiplied by p raised to r q raised to n minus r. In this, n and p are the parameters of the distribution. N is the number of trials and p is the probability of occurrence of an event. So, n and p are considered as the parameters of the distribution. P and r is the probability of occurrence of an event exactly r times in n trials. We are telling probability of getting a head r times in n trials, that is considered as success. Then failure is, that is probability of getting tail in n minus r numbers out of n experimental trials. So, we do not have to separately mention what is the probability of failure. It can be written as 1 minus probability of success. That is why total number of trials or total number of experiments n and the probability of getting a particular event, that is represented r times. So, that n and p are considered as parameters of distribution. Now, PNR is the probability of occurrence of an event exactly r times in n trials, that is probability of a random hydrological event. That is, if we are considering rainfall, in that case probability of getting a rainfall of given magnitude occurring r times in n successive years. Sometimes based on the value of rainfall, we can tell whether there will be a flood or not. We commonly use a term related to probability of exceedance. What is meant by probability of exceedance? It is the probability of occurrence of an event for which the value is greater than certain set point value. We are having certain rainfall value. Beyond that, if rainfall is occurring, we will be considering it as chances of flooding is there in that particular year. So, that way by analyzing the rainfall data, you can find out the probability of getting a rainfall which is more than that of the set point value. So, based on that, we can tell there may be a flood or there may not be a flood. So, that probability is termed as beyond certain set point value it is coming, then it is termed as probability of exceedance. So, this PNR is giving us the probability of exceedance. And small p is the probability of occurrence of an event. Whether there is a success, that is represented by small p. Then Q is the probability of an event not occurring in the given year, that can be represented by 1 minus p. This PNR represents the binomial distribution. Now, let us move on to the cumulative probability, that is the probability of occurrence of an event r or fewer times in n successive trials can be found as the cumulative binomial probability. That can be represented as Px less than or equal to r is given by summation of I is equal to 0 to r NCr p raised to r q raised to n minus r. We are calculating the summation, which is summation of the probability mass function. That is, this binomial distribution is corresponding to discrete random variable. In that case, we will be calling the relationship by means of probability mass function. Cumulative of that will be giving you the cumulative distribution function. That is given by this expression. P capital X is our random variable. It is taking the values less than or equal to small r. That r is the value which we are considered for the occurrence of an event exactly r times in n number of experimental trials. So, Px less than or equal to r is given by sigma I is equal to 0 to r NCr p raised to r q raised to n minus r. So, this much about the binomial distribution and cumulative binomial distribution. Now, let us move on to the descriptive statistics related to binomial distribution, that is descriptors of the binomial distribution. By taking appropriate moments of the binomial distribution, we can get the descriptive statistics related to a particular distribution. All these descriptors are calculated by considering the moments of the distribution. That is, in the case of mean, we have considered the first moment with respect to origin, and other descriptors such as the variance, skewness and kurtosis, those are the moments taken with respect to mean value, not with respect to origin. So, the mean in the case of binomial distribution, mu is given by NP, variance sigma square is NPQ, and standard deviation sigma, we know it is under root of variance, that is under root of NPQ. These are the descriptors of the binomial distribution. Now let us move on to the next distribution, that is Poisson distribution. Poisson distribution is the limiting form of binomial distribution. That is, in this case we are considering P to be very small. Probability of occurrence of a particular event is very small, but the number of experiments or number of trials considered is very large. N is very large, so that we can get NP tends to constant. P value is very small, at the same time N is very large, so that product of N and P will be tending to a constant value. Poisson distribution is given by the function Px is equal to small x lambda raised to x e raised to minus lambda divided by x factorial. In this, lambda is greater than 0, x is taking the value 0, 1, 2, 3 that way. So, Poisson distribution is given by the expression lambda raised to x e raised to minus lambda divided by x factorial. This is the limiting case of the binomial distribution. Lambda can take the value greater than 0. In this case, lambda is given by NP, that is considered as the parameter of the Poisson distribution. This is named as shape parameter. Shape parameter of the probability distribution. In the case of Poisson distribution, the shape parameter is given by lambda, that is nothing but NP. This indicates the average number of events in the given time interval. A certain time interval is considered. Within that interval, how much is the average number of events, that is considered as the value lambda is equal to NP. Now let us move on to the descriptors of Poisson distribution. Descriptors of the Poisson distribution, mean is lambda and variance is given by lambda. Both mean and variance are given by lambda, n multiplied by p. In the case of Poisson distribution, it is a limiting case of the binomial distribution. Different descriptors are there, that is mean, variance, standard deviation, coefficient of skewness, coefficient of kurtosis, all those things are there, but I am not going to higher moments. I am talking about first and second moments only, that is the mean and variance. In the case of Poisson distribution, mean is lambda, that is the parameter of the distribution, and the same as that of the variance. So, these are the two distributions related to discrete random variables which we use in hydrology. Some others are also there that you study when you go in advanced level. So, here we have seen two discrete probability distribution functions, that is binomial distribution and the Poisson distribution. Now, let us move on to the continuous probability distribution functions. First one we are going to discuss is exponential distribution. Exponential distribution is used to determine the length of the time interval between the occurrences of the events. For example, flood. That is, it gives an idea about length of the time interval between occurrence of two flood events. Exponential distribution is given by the function f of x equal to lambda e raised to minus lambda x. Since this is for continuous random variable, we will be expressing by means of probability density function. Probability density function is expressed as small f of x. That probability density function corresponding to exponential distribution is given by lambda e raised to minus lambda x. While talking about the values of lambda and x can take any value greater than 0, lambda can also take any value greater than 0. When we talk about hydrologic variables, majority of the hydrologic variables are positive. Rainfall value, stream flow value, evaporation value, all these values are positive. So, in the case of exponential distribution, x and lambda are greater than 0. Now, coming to the cumulative distribution function of exponential distribution, That is, if we know the probability density function, integral of that probability density function will be giving you the cumulative distribution function. So, CDF is given by capital F of x equal to 1 minus e raised to minus lambda x. You integrate the probability density function, you will get the cumulative distribution function, that is given by 1 minus e raised to minus lambda x. Now, next details which we need is related to descriptors of the distribution. Coming to the descriptors, first one is mean. Mean of exponential distribution is given by 1 by lambda and variance is given by 1 by lambda square. So, in the case of exponential distribution, we have seen the probability density function and the corresponding cumulative distribution function. Mean is given by 1 by lambda and variance is given by 1 by lambda square. If variance is 1 by lambda square, standard deviation will be 1 by lambda. Now, coming to the next probability density function corresponding to continuous random variable, that is gamma distribution. Gamma distribution can be used to determine the time to the nth event. So many events are occurring, independent events. So, time to the nth event can be obtained by making use of gamma distribution. It is given by the function f of x equal to lambda raised to n x raised to n minus 1 divided by gamma n multiplied by e raised to minus lambda x, for which x is greater than 0, lambda greater than 0, n can take any value 1, 2, 3 that way. So, fx is given by this expression, that is probability density function related to gamma distribution is given by this function. Gamma is gamma function, this we have seen while explaining Nash model. So, gamma n is given by n minus 1 factorial. Gamma n value can be, if n is an integer, we can calculate it by taking the n minus 1 factorial. And the probability density function can be obtained by means of this expression given by fx. Now, coming to the descriptors of the distribution, for gamma distribution mean is given by n by lambda and corresponding variance is given by n by lambda square. In this case, you can compare it with the exponential distribution. Exponential distribution, the descriptors were found to be mean is 1 by lambda, variance is 1 by lambda square. Here, for each event, equal weightage is given, that is why mean is given by n by lambda and variance is given by n by lambda square. Now, we will move on to the next continuous probability distribution, that is the one which is commonly used in hydrologic analysis, which is termed as normal distribution and also Gaussian distribution. So, Gaussian distribution is very common in hydrologic analysis. It has got a symmetrical bell-shaped probability density function. Probability density function can be schematically represented by means of a bell-shaped function which can be schematized like this. Our probability density function is along the y-axis and along the x-axis the values of x is given, and if you plot the PDF, it will be looking like a bell-shaped function. This is very important function which we commonly use in the hydrologic analysis. As the number of years, we are considering the annual rainfall data and we are trying to fit some probability distribution for those data. In that case, if the data is of annual data, then we can make use of normal distribution. But in other cases, that is if we are dealing with the hourly rainfall data or daily rainfall data, we cannot make use of this particular distribution. This is a symmetrical bell-shaped probability density function and the function is given by f of x is equal to 1 by sigma under root of 2 pi e to the power of minus 1 by 2 x minus mu by sigma all square. The range of these distribution, that is x is between minus infinity to plus infinity. But majority of the hydrological variables are positive. Rainfall, either there won't be any rainfall, 0, or after that it can take any value, any positive real number. So, the value will be between 0 and infinity when we talk about hydrology variables. But in the case of normal distribution, the range is between minus infinity to plus infinity. So, the function is given by 1 by sigma under root of 2 pi e to the power of minus half x minus mu by sigma all square. X varies between minus infinity to plus infinity. Now, this x minus mu by sigma can be represented by means of z. Z is equal to x minus mu by sigma, and if we substitute in that particular expression of probability density function, expression will be simplified. So, Z is equal to x minus mu by sigma, and the Z is termed as standard normal variate. If we can write the probability density function in terms of standard normal variate also, that is in terms of Z. Now, coming to the parameters of the distribution, that is mu is equal to x bar, that is mu is the population mean and x bar is the sample mean. Population mean can be represented by means of sample mean, and sigma is the standard deviation corresponding to population, and S is the notation used for the standard deviation in the case of sample. So, in the case of normal distribution, we can consider the population mean and population standard deviation as the sample mean and sample standard deviation. That is, this is parameters in terms of sample moment. Mu is equal to x bar and sigma is equal to S. In this case, mu is the location parameter and sigma square, that is the variance, is the scale parameter. Mu is the location parameter and variance sigma square is the scale parameter. Based on this, where the mu is there and mu is representing the average value, and also the variance sigma square is representing the dispersion in the data. So, based on this mean value and the dispersion value, sigma variance value, we can understand how the shape or how the data is spread. The details related to data can be understood by going through the shape parameter and the location parameter. So, that much about normal distribution. Very minimal description I am giving over here. Now, for example, in the case of annual precipitation, we commonly make use of normal distribution as the probability distribution. Annual precipitation, that is calculated as the sum of the effects of many independent events, tend to follow normal distribution. Many independent events means each and every day's rainfall is independent of the previous day or next day's rainfall. So, annual precipitation is calculated as the sum of the daily precipitation. So, that usually follow the normal distribution, but it is not the case with the daily precipitation or hourly precipitation. In that case, we cannot make use of normal distribution. Now, next one is the extreme value type 1 distribution, which is termed as Gembel's distribution. When we talk about hydrologic analysis, extremes are too common nowadays, that is occurrence of a flood. During the monsoon season, majority of the places are getting flooded and urban cities are very commonly getting flooded. Rivers are overflowing, flooding in that entire area is taking place. So, extreme events are very common in monsoon season. At the same time, during non-monsoon season, drought is also a common phenomenon. So, the scarcity of rain and also abundance of rain. So, these two extremes are very common. For analyzing these type of hydrologic variables or hydrologic analysis involved with these extreme values, we need to go for extreme value analysis. For that, we commonly make use of extreme value type 1 distribution, Gumbel distribution. Extreme value type 2, type 3 distributions are there. So, those I am not covering over here. I am going to discuss about only the extreme value type 1 distribution, that is Gumbel's distribution. It is widely used in hydrology, very commonly used in hydrology, and the probability density function is given by f of x equal to alpha e to the power of minus alpha x minus beta minus e to the power of minus alpha x minus beta. So, this is the probability density function corresponding to Gumbel distribution. This is very commonly used in hydrologic analysis, especially in the case of frequency analysis. X can take the value between minus infinity to plus infinity, and coming to the cumulative distribution function, small fx is representing the probability density function of Gumbel's distribution, and cumulative distribution is given by capital F of x equal to e to the power of minus e to the power of minus alpha multiplied by x minus beta. So, cumulative distribution is given by this function. In this, alpha is the scale parameter, it can take value greater than 0, and beta is the location parameter, it can take values between minus infinity to plus infinity. The scale parameter and location parameters are described by alpha and beta in the case of Gumbel's distribution, and we have looked into the probability density function and also cumulative distribution function in the case of extreme value type 1 Gumbel distribution. And this we will be making use and we will be studying more into this type 1 distribution when we discuss about frequency analysis. So, these are the very commonly used distributions in hydrology as far as discrete random variables and the continuous random variables are concerned. So, very minimal way I have covered in this lecture. You can go through these references for getting more understanding. So, here I am winding up this lecture. Thank you very much.